Hi everybody! Welcome to video 4.3, Graphing Rational Functions. This is part 2. It only contains one example. You're going to have to watch the video for part 3 to get the second example of graphing rational functions. Now, our objective is to graph the rational functions with more than one asymptote. So these are getting into the more complicated ones, which is why we can only put one on each video. We're going to be looking at finding asymptotes, intercepts, points of discontinuity. We're also going to look at some properties, domain and range, increasing and decreasing intervals, as well as end behavior. Well, let's continue. In our first example, we're going to look at it from the point of view of can a graph have more than two branches? So far, each graph that we've worked with has had only two branches, but there are some with more. We're starting with the function given here, f of x equals 2x squared plus 5 divided by x squared minus 25. Remember, our very first step is always to factor and, if possible, cancel in order to simplify. Notice that our function here does not factor on top. However, it does factor on the bottom. That's a difference of squares, so we get x plus 5 and x minus 5. Now, it has factored, but nothing has canceled. Therefore, we know we have no point discontinuity on this graph. Of course, we have other types of discontinuities. We have asymptotes, and those are infinite discontinuities. We're going to find our vertical asymptotes first. Remember, in order to find a vertical asymptote, you want to set your denominator equal to 0 and solve. In this case, we've already factored our denominator, so we're going to set each factor equal to 0. X plus 5 equals 0. Subtract 5 from each side, x equals negative 5. X minus 5 equals 0. Add 5 to each side, x equals 5. Let's place those vertical asymptotes on our graph. The first one at negative 5, and the second one at positive 5. Now, let's look to see if we have any horizontal asymptotes. Remember, we use the analogy of the snowman to find our horizontal asymptotes. We look to see if it's top-heavy, bottom-heavy, or even on the top and bottom. What we're really comparing are the powers of the highest degree term in the numerator and the power of the highest degree term in the denominator. In this case, notice they are highlighted. They are both 2. We call the n, if you like, the power of the numerator, 2, and d, the power of the denominator, 2. In this case, they are even. And when they are even, we use the coefficients. We sometimes say y equals a over c, where a is the coefficient of the highest degree term in the numerator, in this case 2, and c, the coefficient of the highest degree term in the denominator, in this case 1. Therefore, we have a horizontal asymptote at y equals 2. Let's draw that in as well. Guys, I know I'm talking kind of quickly, but remember, if you need to stop and take notes, you can pause at any time. The next thing that we'll need to do is find our intercepts. Remember, the x-intercept occurs where y equals 0, and the y-intercept occurs where x equals 0. So we just need to find those values. In order to find the x-intercept, and as long as there is no k value, remember k is the term that is sometimes added at the end of a function, as long as there is no k term, and there isn't in this one, we can set the numerator equal to 0 in order to solve. Now, to set the numerator equal to 0 and solve, we need to do 2x squared plus 5 equals 0. Subtract 5 from each side and we'll get 2x squared equals negative 5. We're going to divide each side by 2. We'll get x squared equals negative 5 halves. And in order to get x, we'll have to take the square root of both sides. Notice that what's happening here is that we're trying to take the square root of a negative number. Well, we can't get a real answer doing that. Of course, we could get an imaginary answer, but that's not going to help us. So we're going to say that there is no x-intercept. Now, can we find a y-intercept? Well, remember, the y-intercept occurs where x equals 0. So we're going to go back up to our original function. We're going to plug in 0 for x squared, and we're going to see what's left. Well, notice that 2x squared disappears, and the 1x squared in the bottom disappears, and we end up with 5 over negative 25, which simplifies to negative 1/5. Therefore, our y-intercept is at 0, negative 1/5. Let's go ahead and put that on our graph. 0, negative 1/5 will be on the y-axis just below the origin. Well, we have 1 point on our graph. I think we're going to need a few more. The rule of thumb here is to have 2 points between each vertical asymptote, or on each side of each vertical asymptote. Since we're in the middle of the graph, let's just stay there right now, and let's see if we can find a couple of values. Let's use 1 and negative 1 and see what happens. Now, plugging 1 into our function, 1 squared is 1, times 2 is 2, plus 5 gives us 7 in the numerator, and then 1 squared minus 25 is negative 24 in the denominator. Notice that we'll get the exact same thing if we plug in negative 1, since that negative 1 is going to get squared. So in both cases, we are at negative 7/24. I'm going to put those 2 points in as well. Now, they are just below the negative 1/5 that we already had in there. But now we have enough points that we can sketch this portion of the graph. Remember, what the points allow us to do is we're going to connect those, and then we're going to use our asymptotes as a guide. Our graph is always going to approach the asymptotes. If you want to say, hug the asymptotes. It can run alongside, but in general, it cannot cross, and we'll talk a little bit more about that later. Well, we have the middle of our function, but what do we know about the right side and the left side? The only way we're going to find anything out is to plug in some values. So let's look to the right of our right asymptote, which is at 5. I'm going to choose the values 6 and 7. If I plug in 6 squared is 36 times 2, 72, plus 5 is 77. In the denominator, 6 squared is 36 minus 25 is 11. Well, 77 divided by 11 is 7. So 6 on the x-axis and 7 on the y. That gives us a point right about there. Let's plug in 7 and see what happens. 7 squared is 49 times 2 is 98 plus 5 is 103. Divided by 7 squared, 49 minus 25 is 24. Well, that's approximately 4, a little bit more. So at 7 on the x-axis, we'll be at a little bit more than 4. Now we have 2 points. If we just connect those 2 points and approach our asymptotes, we will have the branch on the right side. And there it is. Remember what we said. If you plug a negative value in, you get the same answer as the positive. So if I plug in negative 6, I'm going to get the very same answer because my negative gets squared. So I'm going to have the same value all the way on the left. So I'm going to put a point here at 7, and then another point here just above 4, where we had it. And now I can draw in my last branch. And there it goes. That's our complete graph. Looks pretty good, don't you think? So when do we have enough points? We have enough points when we have at least 2 on each side of each vertical asymptote. All right, now let's quickly look at some properties of this graph. Let's take this away, and there it is. Same graph, if you notice, asymptotes at 5 and -5, and also horizontal at 2. We're going to look first at domain. Remember, domain goes from left to right. From left to right, we have all the way negative because we have an arrow going forever to the left. So we're going to start at negative infinity, and notice our graph goes up to the first asymptote, and it stops there, or it continues, but it never goes past -5. So we're going to say to -5, open at -5, and then we're going to let it pick up on the other side of the asymptote at -5, continue all the way to the second vertical asymptote at 5. Notice it never reaches 5, so that is also open. And then it picks up on the other side of that vertical asymptote at 5 and continues forever to the right. Now looking at range, remember it works the same way. We ask the question how far down and how far up. This graph we can see is going forever downward, so that's negative infinity. But this is slightly different. It goes up and it reaches a maximum value at our y-intercept. Well, what was the value of that y-intercept? I believe it was -1/5. Because this value is included, we're going to give it a square bracket. Now, we do have other pieces of this function, and so remember, we're going from bottom to top. Where does this function pick up again? Not right after -1/5, but where? Right after the horizontal asymptote. The horizontal asymptote is at 2. Remember, we never touch it, so we are open at 2, and then we continue upward forever and ever, or to infinity. Our end behavior, remember, this is asking what the graph does in the left end and in the right end. So looking at left end behavior, so I'm going to write as x approaches negative infinity, what does our graph do? Our graph, f of x, is approaching the horizontal asymptote at 2. For right end behavior, I'm actually seeing the exact same thing. As x approaches infinity, our graph, f of x, is approaching the horizontal asymptote again at 2. One last look at this graph. If the pre-cal pest is traveling left to right, as we do with graphs, is he increasing or decreasing? And is it over the whole domain? Well, in the very left branch, notice that from left to right, he is increasing. How about on the bottom portion of the graph? Again, from left to right, he is climbing uphill. What happens once he reaches the maximum, though? He gets to start going down. So there's a decreasing portion to our graph. And then again, past our vertical asymptote, if you were crawling down this branch from left to right, he would be decreasing. Okay, that was a quick look at our first, more complicated rational function. This one had 2 vertical asymptotes. I don't think it was that hard. I hope you did well. Remember, you can pause it, you can go back and do it again, or you can go on to part 3 and see the next example. See you on Monday.